Hi everyone, my name is C-Dubs. I just graduated high school. Um, that's pretty much all you need to know about me. Today we'll be going over limit laws and continuity. So today we're mainly going to be evaluating limits. So in other videos we've talked about continuity or differentiability, and we've talked about the definitions of those and how to find out if a function is continuous or not using limits. But in this video, we're just going to be evaluating the limits themselves. And in that case, we will just, the limit will be equaling the function value. So we'll talk about that a little bit before we get started. And then once we get into the groove of things, it'll be a lot easier. So something, basic thing that you need to know when we're talking about limits is just the definition of continuity. So if a function is continuous at x equals a, to find the limit as x is approaching a for the function, you just plug in. So this is kind of like just what you do when you're evaluating limits. So first, if we just real quick remember the definition of continuity, basically it means the value that you're approaching is actually there. So we know that there are some cases, like if there is a hole in a function where you've got a function and it's going, and then say it's approaching like 1. At 1 there's a hole and the actual value is like somewhere up here, but not where the function was approaching. A little confusing, but basically with the limits, if it's continuous, then the value that you're approaching is actually there. The point is there. But if it's not continuous, then the point will be somewhere else. Or maybe there won't be a point there. But that's just, for continuity, the value that you're approaching is actually there. So since it's actually there, then we can just plug in numbers and whatever it equals is the limit itself because it's continuous. So for evaluating our limits, we will just plug in and that will give us our number. So it's relatively simple. All right. So our first problem. Since we're just plugging in, the first couple of problems are pretty easy because it's just plugging in the value for x. So for the first one, we plug 2 into x. 2 is 2. For this one, there isn't anything to plug into here because we're plugging a into x. Since there's no x, we just keep the same number since there's nothing to plug into. So 4, 4. Okay, this one, sorry, some of it is cut out, but there we're plugging in the 2, plug 2 into t. T is our kind of x in this situation. So we're plugging in 2, 4 times 2 is 8, 2 plus 3, 8 minus 1, 7, 2 plus 3, 5. So there you go. Okay, our next one, we're plugging in 27. This one's a little harder just because we're talking about exponents, and exponents can get a little tricky. So on exponent ones, it's a little easier if you kind of break it down and write it in a little different way. That can make it easier. So I think I will attempt to break it down. Okay, so the exponent is 2/3. We've got that written down. And then just to try to break it down a little more, I'm going to rewrite it a little differently. So here, I took out the 2 and squared the whole thing. And then I'll break it down a little more to make it, to show you more easily. Oh, except oh no, I didn't. I thought the video was paused because my hand was moving, but I was just that still. Okay, so 27, if you take the cubed root of 27, the cubed root of 27 is 3. So basically here, 3 to the 3rd, we plugged it in the place of 27, and then the 3's cancel out. So then this whole thing right here is just a 3, and then so it's 3 squared, and then that equals 9. So that 9 is there for the 27 to the 2/3, and then minus 9 over 27, which we simplified to 1/3. And there you have 26/3. All right, this next one. Oh, we're plugging in pi now. So 2 plus sine of pi. If you know your unit circle, you know sine of pi is 0. And then plug in pi into x again, pi squared. So 2 plus 0 over pi squared. And you have 2 over pi squared. There you go. So evaluating limits is a lot nicer than some of the other things that you have to do with limits, like proving continuity and things like that. All right, so we're given some givens. We're given some givens. Okay, sorry, but we have some givens at the top to use here. So again, we're just plugging in and we'll use the givens that we have. So here we plugged in -2 into the x here, g of -2. And right here we're given that the limit as x approaches -2 of g of x is 3. So if we kind of ignored the bottom part, we'll see that that is equal to this. So we just plug in 3 there. And then we're plugging in our -2 into the x's, -2 squared plus -2. So 4 minus 2 is 2, 3/2. All right, number 7. We're going to use our givens again. We see this here. This is this. So we can plug in -1. And we've got -1 plus 1. That's going to equal 0. We used our given again here, but it doesn't matter as much since the top is 0. So just the whole problem is 0. But we plugged in our 3. All right, number 8, again, using our givens, we've got our -1. So 3, we put in -1 squared. So -1 squared is 1. 3 times 1, and then using our given again. Oh, 3 times 3, 9. Okay, there we go. But plugging in is nicer. All right, number 9. What is the definition of continuity for a function at a point x equals a? So we covered this in our continuity and differentiability video, and if you want kind of a better explanation on it, or something more in-depth or practice with continuity, then you can go check out our other videos because we have more in-depth videos about continuity, since this video is more about evaluating functions. But we'll quickly go over the definition right here just for the next section. So the limit as x is approaching a from the left, so the negative above the a means that it's approaching from the left side. Oh, or maybe left would be over here. The camera's switched, so it looks weird. So this is the limit as it is approaching a number from the left, and then this is the limit as it is approaching a number from the right. So approaching, and then, oh, it's kind of blocked out. You can't really see it, but the left side approaching and the right side, those values, those limits have to equal the number as a whole. So there's a left side, there's a right side, and then there's just what the function itself is approaching in general. So these two have to be equal to each other for the value to be continuous. And we'll get into that a little more. I tried to rewrite it right here, but it's kind of blocked out. I'm sorry about that. And then we have the limit as x is approaching a number of the function is equal to the function itself. So this is the definition of continuous, but just remember that in order to have this part of the definition, the left side and the right side must be equal. So if, for example, there's a function and the right side is up here and the left side is down here, they can't really reach the same value. I don't know if that's a good example, but like they have to be approaching the same number. And if they're not approaching the same number, then the function cannot be continuous. So you have to make sure that the left and the right are equal so that you can have this number. And then once you have this limit, if the limit is equal to the function itself, then the function is continuous. I think that's pretty good. It's the whole, like, you're drawing a function, and if you never pick up your pencil, then it's continuous. Which isn't necessarily always true, but it's a good example in this context. And for calc classes, A, B, and BC, it works. Okay, so we're finding where the function is discontinuous, and then we're classifying the discontinuities. So basically what we're doing, a lot of these functions have drawings that go with them. So I'm going to be drawing the function itself, and then we'll talk about the type of discontinuity. Real quick, I'll just go over them. So there are 3 types of discontinuity, but you don't really need to worry too much about it. And we won't even talk about one of them, but just know the different types of, there are a couple of different types. And yeah, this is when you're lifting up your pencil. Like you're drawing a function, you lift it up. So the part where your pencil is not touching the paper, you could say. The main 2 that we'll talk about is removable and infinite. But I'll show you examples. It'll be easier to understand. So here's the graph. Right here is an asymptote, and that asymptote is at x equals 0. So since if you were drawing the graph, you would have to lift up your pencil to go up here, and the 2 functions, the 2 parts of the function don't connect, then we know that it's not continuous. This kind of discontinuity is infinite discontinuity, because they are going infinitely in that direction and infinitely in that direction. So a vertical asymptote is an infinite discontinuity. The graphs don't really matter, but the graphs make the discontinuities easier to visualize. So it's kind of easier to just see the discontinuities. All right, this other type of discontinuity. So this is absolute value, as you can see. Okay, so the absolute value. Sorry about that. So here we've got it. As you can see, if my little cursor were a pencil, I'm drawing all the way on the line and I never pick up the pencil. There are no holes, no asymptotes or anything. So that means that it is continuous everywhere. All right, this next one. So here, it'll be easier if we factor out everything, simplify it. So we did that. We have x plus 1, x minus 3. And here, since these are the same, you cancel them out. So you have, when you have things that you can cancel out, something on the top, something on the bottom, they match, then that means you have a hole at that spot. And a hole, it means that the function itself is not continuous. And then when you have a hole, it means it's a removable discontinuity. It's that one single point that is not continuous, that one single point that makes the function not continuous, as opposed to an asymptote, where an asymptote goes like forever in either direction. Holes are that one point. And then we have x equals 3. X equals 3 is a vertical asymptote. And vertical asymptotes are infinite discontinuities. See where x equals 3 is just on the bottom? Well, x minus 3, and then we solve for 0. We set it equal to 0 and solve for x, sorry. So holes are when we have the same thing top and bottom and we can cancel them out, and then asymptotes are when it's just the one thing. So here, again, the graphs are not necessary, but it's easier to visualize and then easier to like get the concept of, but wow, this is difficult. So here's the hole. Again, it doesn't make the function go forever in either direction. It's just that one little point, and then the function is continuing. But here we have the asymptote, and that's where they're going forever in the different directions. So that's where you can kind of see the infinite versus removable. Right. We've got a tangent here. So tangents have their own graph-looking thingy as well. I think I got kind of confused here for a second, so maybe I don't know. So right here, what we're doing is we're trying to find the endpoints for the function because tangent repeats over and over and over again because it has all these asymptotes. So we're trying to find the asymptotes. That is wrong. I was messing up. But basically what you have to do when you have a tangent or a cosine or sine or whatever, you have to find the endpoints. And what you do is you set it equal to pi over 2. Well, it depends on which trig function it is. For tangent, you set it equal to pi over 2. You set whatever is inside the parentheses. So since we have x over 2 there, oh no, my hand. Oh well. So since we have x over 2 here, we set it equal to pi over 2 because it's tangent, and then we solve for x, so you can do it however you want if you want to cross multiply or whatever, but x equals pi. And then you have to also set it equal to negative pi over 2, so we have x equals negative pi, and so those are our endpoints for the functions. And these are going to be our asymptotes since tangent repeats a million times forever. So again, drawing the graph to help with visualization. So there's one asymptote, and then we have the other asymptote on the other side, and there's our tangent graph. And then since we have these asymptotes, we know it's discontinuous. And if you can guess, I'm sure maybe you know by now, since we've talked about it, but asymptote means infinite discontinuity. So it's a vertical asymptote, so it has infinite discontinuity because they're going forever in either direction. So there we have it for tangent. And again, I could keep drawing these forever, but you obviously will not do that, so. Okay. Okay, so number 14. Prove that the following function is continuous. So again, if you want more practice on problems like this, where you're finding if a function is continuous, we have another video on that. But this video is more, it covers a number of different topics, so we're covering this as well. But if you want more practice, we have videos on that. But here we go, we'll cover this one. So our steps for when we're finding if a function is continuous or not is we want to look at the left side, and then we want to look at the right side, and then we want to look at the function itself. So first I wrote the left limit, and then I'm going to write the right limit, and then the function. If you remember, this has to do with the definition of continuous that we were talking about at the top of this sheet. So we have to find what the left limit is and what the right limit is. And if I moved my hand, it would be easier to explain. Okay, so right here, since we have x is less than 2, then that's the left side because that's the side that's going negative forever since it's less than 2. So it'll be from the left, and x squared plus 3 is what we have for this, what do you call it, a range? Bounds? Bounds? Okay, anyway though. So since this is less than, we're going to use this. We'll put it here for the limit, so we can use this, and then we'll be plugging in 2, since 2 is our split point. But yeah, 2 is our A. It's where our function is approaching. And then for the right side, this was x is greater than or equal to 2. So since it's greater than, it's from the right side. We use the function here. We plug it in. We plug it in for f of x. And then again, we'll plug in our 2 to solve. So here, oh, well, okay. We did the 2 squared is 4 plus 3 is 7. And then here, 2 minus 2 is 0. E to the 0 is always 1. And then 1 plus, we plugged in our 2, so 3 times 2, 1 plus 3 times 2, 1 plus 6 equals 7. And then if you see here, this is an equal sign. So for the function itself, we always want to use the equation that has the equal to. So we would use this same equation. So it'd probably be better for you to write the equation again and then plug in again. But I got lazy, so, but it would be the same process as this right here. And that also equals 7. And if you remember at the beginning of our video, the left and the right side have to equal each other for the limit to equal the function. So our left and our right sides are equal, which is good. That means that the function exists and is continuous. And then the function equals the left and right limits. Okay, I'll try to explain clear real quick. Okay, so the left and the right limits equal each other, which means that the limit as x approaches 2 is a thing and exists. And then since these are 7, we know that, I'm about to write the sentence, but since the limit as x approaches 2 is equal to 7, since these are both equal to 7, and the function itself also equals 7, then the function is continuous since the limit equals the function. Oh, wow, I wrote it. Nice. Okay. So, and then we have our nice sentence that makes sense that I will write right here. Okay, I wrote it. There we go. So f is continuous at x equals 2 because the limit as x approaches 2, there's supposed to be 2 there. 2. Because the limit as x approaches 2 for the function equals f of 2, which equals 7. So the limit equals the function, which equals a value. So it's continuous. All right, and then find the value of the constant. So to find the value of the constant, we're going to use our same continuity steps. Since we're talking about continuity again, we have to find the value that makes the function continuous. So we're basically going to kind of prove continuity a little bit. So again, starting with our left side limit and then our right side of the limit. And then we'll plug these values in. So the left side, this is less than. So we're going to use this equation. We'll put it in here. And then since this is the right side, since it's greater than, we'll plug that there. And we'll also simplify by plugging -1 into x. Since a is our constant, and we're looking for a, remember that a is a constant, it's not a variable. Sorry, there was not a lot of room. So I plugged in 1, so we have -a plus cosine of -pi. And we can simplify that a little further because the cosine of -pi, if you know your unit circle, is -1. So -1 minus 1. And then we're doing our right side with the x squared plus 3a. We'll plug in our -1 into the x squared, which will get us 1 plus 3a. And then if we remember before, the left side has to be equal to the right side. So we're going to use the -a minus 1 and the 1 plus 3a. We'll set those equal to each other so that we can find a. First, I think I'll just write the function. If you remember, we have to write that. Oh, this might be not low enough. Okay. You're going to see this little box. I'm sorry. Maybe I can try to move it. Sometimes I just didn't. Yeah. Anyway, so we always have to have the function as well, so just remember to write that. And again, we have to use whichever sign is also equal to. So we'll be using the top equation. And again, this is the same as, oh no. Oh no, why did we use this equation? That is not right. Okay, that's not right. I wrote the wrong equation. Always good to check yourself. So for the function itself, you always want to use the equal to. So I should have written the top equation, not the bottom equation. Oh, well, I guess. So ignore that. If you want to write, if you're doing this with me, you would write this equation on the paper, and then you would do this whole thing again, and you would have -a minus 1. And then, as I was saying earlier, we set the equations equal to each other. Negative a minus 1 equals 1 plus 3a. And then we subtract the 1, add the 3, negative 2 equals 4a. Divided by 4, a equals negative 1 half. Woo! And then we will write our nice little sentence. At some point, I'm sure I'll get to writing it. Wow, it took me a while. Okay, here we go. So if a equals negative 1 half, then f of x is continuous at x equals negative 1 because the limit as x approaches negative 1 of f of x is equal to f of negative 1. There you go. There is our sentence. So there you go. Again, as I was saying earlier, if you want to do more practice on continuity or differentiability, we have videos on that, and they're probably a little more in-depth than this one. But as you can see, evaluating limits on their own is generally pretty simple. It's just plugging in. The continuity is a little harder, but you'll get the hang of it if you haven't already. Yeah, that's all I got for you. Thank you so much for joining. I hope this was helpful for you. We have lots of videos on a lot of different stuff, so if you have any other calc questions, feel free to browse the channel, look for a different video. I'm sure we have it. And that'll be all. See you next time.